Okay, so we're going to talk about optimization for deep neural nets. So we really just so far talked about different neural net architectures, which is really just defines a class of functions. For example, we had an architecture which had a single fully connected layer, which said that our output function in the regression context, it has some parameters theta, f sub theta. Say, for example, this is equal to beta transpose some sigmoid applied to some other weight matrix, W transpose X, plus some weight vector W naught, plus some beta naught. Right? So this is, let's look at the dimensions of all of these tensors. In general, these are going to be tensors, but most of these are vectors and matrices. So whatever our output space is, so if our output space is, so our input space has dimension p and outputs, perhaps there are k of them. For example, if we're doing k-class classification, then the beta would have to be a matrix. Right? So beta here is, well, the output is going to be k, so this is k by p. So beta transpose is k by p. Right? This w here, it has to be h by p. Oops, sorry, this is k by h. H by p is the w here, w transpose, because it has to map the x space, which is p-dimensional, into the number of hidden units. Now this sigmoid applies element-wise. Oops. And whenever we have some sort of an activation function applied to a vector, just think of it as being applied element-wise. This w naught, of course, is h-dimensional, and beta naught is k-dimensional. Is a k-dimensional vector. So this is sort of what we're going to think of if we're going to be using our neural net to, say, for example, train multi-class classification. And we already talked about loss functions for multi-class classification, and so this really is going to give us a formula, a framework for creating state-of-the-art multi-class classifiers. Okay, so this is just for predict, and this theta, we're just going to use it to denote the set of all of the parameters, so beta, beta naught, w, and w naught, right? In this case, but it of course could be much larger, right? Now, this doesn't give us a loss necessarily that we can optimize. We still have to choose our loss. So, for example, with the multi-class classification, we might have chosen multi-class loss, like the categorical cross entropy. Right? And once we've chosen our favorite loss, then just recall we want to minimize the empirical risk. So the empirical risk, this looks like R sub n of our parameter space theta, of our set of parameters theta, which is equal to 1 over n sum over I L of yi f sub theta of xi. Right? So this is on our training set. This is our empirical risk. And so we've already gone through different methods for optimizing this. For neural nets, typically we're going to be using mini-batch stochastic gradient descent. And so our full gradient this is partial Rn over partial theta, right? Or let's just use one of these. For example, Wj, the jth column of W, is equal to 1 over n partial over partial Wj, of course. Sum over I, partial over partial Wj of the loss, yi f sub theta of xi. Right? And we're accustomed to doing this with linear f, but of course f is nonlinear now. Nevertheless, we can still talk about mini-batch SGD. So for a mini-batch, if we have drawn a sample of n points, then instead we're going to be using the 1 over m, sum over I, partial over partial wj of I going from 1 to little m, partial over wj of this loss, yi f sub theta xi, for a mini-batch sample, for a sample xi yi, I going from 1 to capital M. So this is typically how we're going to optimize our neural nets, is draw a mini-batch sample and then move in away from the mini-batch gradient here. Okay, so now how can we calculate this derivative with respect to wj? Well, of course, the way that we would do this is just use basic calculus, which says that we should use the chain rule. So think about this f sub theta of x here. We would start, for example, by using the chain rule on the loss. And so this partial of a loss, partial over partial, let's just use wjk of the loss of yi and f sub theta of xi. This is equal to L prime yi f sub theta of xi times this partial f over partial wjk of xi. This is just the chain rule and nothing more. Where of course this L prime is just the partial over partial z of L of yi, oops, not f, L of yi f sub theta of xi. Oops, let's make this a function of z. Right? So this is our first step. Now we've reduced our gradient to a function of these losses, and you can, for all of our losses, you can just you can hard code exactly what this L prime function is. So you could say, for example, if we're using the hinge loss, then we're going to use our subgradient of the hinge loss, and you can just hard code that in, which is really just the indicator that yi times z is is less than 1, right? So that's the nice thing. It sort of gives you a hint about how you would create an automated framework for doing these sorts of gradient calculations. Is, for example, when I create an interface to the hinge loss, I would just also create a way of accessing its gradient as well. And then and now I have access to this L prime. But what about this component here? What about the gradient of f with respect to wjk? Part of the challenge is that up here I chose my favorite architecture, the one hidden layer fully connected neural net. But this is by no means the only architecture. And part of the magic of neural nets is that you have a lot of flexibility in the selection of this architecture. You can add convolutional layers, fixed layers like max pooling or pooling layers, and then you can do a lot of things with the architecture like create recurrence and so on. So we really want a method of taking these gradients that can adapt to different choices of architecture, which really just is different choices of functions here. right? Different function classes. Okay, well, let's do a little experiment in this example. Let's think about the partial of f sub theta of xi with respect to wjk. Right? This is equal to the sum over L going from 1 to capital H of beta little l here, and L is, let's use iota. Iota. Okay. And then the gradient with respect to w jk of this hidden unit, which I'm going to write at h sub iota of xi. But this h sub iota, I'm just going to define it to be this inner part, right? So the output of the hidden unit. So this is where h sub iota of xi is equal to the sigmoid of w transpose x plus w naught. Right? Okay, so far so good. Now let's continue this this partial over partial wjk of h sub iota of xi. This is equal to, just let's apply the chain rule again. Sigma prime, the derivative of sigma, because it's univariate, we can just, and it's applied element wise, this is another thing that we can just cache. Right? We can cache this, and I'll show you what I mean in a minute. Okay, of this w transpose x plus w naught times the derivative of this w of this inner part here with respect to wjk. Right? But this derivative really just ends up picking out the column of w here and then multiplying it by xk if iota is equal to j, and then 0 otherwise. This iota is not equal to j. Now, did we have to go through this whole process? Right? Like, for example, if I gave you an architecture and you needed to calculate its gradients with respect to all of its parameters, it would be very cumbersome. First, you have to look at all of these matrix multiplies in linear portions and figure out what their gradients are. Right? And then you have to take the activation function, figure out what its derivative is, or gradient is, subgradient perhaps, and then apply that function to the inner part, and then also apply the chain rule here. Right? So did we have to do this? Well, in some sense, we can automate this entire process. Right? And this automating the derivative process is called back propagation. And the basic idea is that suppose we wanted to calculate, for example, just the gradient with respect to, let's do something simpler, f sub theta of xi over partial beta. Let's call it beta sub j. Right? Suppose this is what we wanted to do. Well, that's equal to the sum over, well, that's just going to be equal to the h sub j of xi. If we just think about this top component, it's just a linear function in the h's. Right? And so the basic idea is that to get the gradients, to get some grads, we need the evaluation of the hidden units. Okay. And so the first step, if we want to do gradient descent, is to do the forward step. Right? Therefore, the first step is the forward step, where we evaluate all of the hidden components. Right? Where we evaluate the hidden units. So, for example, this hj of xi. That's the first step. And then if we have a deeper neural net than just a single hidden layer, then we're going to have to evaluate all those layers. And if you look at, for example, the gradient with respect to the loss, if we took, if we had a tunable parameter in the loss, for example, you could almost think of the intercept as a tunable parameter in the loss, then we would just need the f sub theta of that final intercept, the beta naught. We would just need that f sub theta evaluated at xi. So we would even need the output. So the first thing we do is this forward step. Now, once we have all of these hidden units evaluated, we now need to go back and calculate all of these gradients in sequence. So we would start with the betas. We would calculate its gradients in this way. And if there was an activation function or nonlinearity, such as the softmax that happened before this f sub theta, say for example the outputs were the probabilities for a categorical for multi-class classification, then we would need that we would need to calculate the gradients with respect to the betas. We would need these hidden units, and then we would go to the trainable parameters in the next layer, right? So the w's are the trainable parameters in the next layer down, and then we would calculate the gradient according to equation star. So let's think about this in terms of a computation graph. So our computation graph, the partial of f of xi over partial of wjk, this is, well, we just need to compute it. So first we're going to think about making the forward pass. So as x goes to calculating h, which is our first fully connected layer. So it's a fully connected layer, which the output of this is the h. Right. And then we have a linear layer, right, which the output of that is the f, right? And then we can calculate the loss, right? And y was also used to calculate the loss. And all of these layers have their internal tunable parameters. So we do this forward pass in our compute graph. We get the fully connected layer, so the h's are calculated, linear layer, so the f is calculated. That goes in loss. The losses are calculated. And then from the loss, we can calculate L prime. In addition to the loss, we can calculate L prime. And the linear layer was required to the activation, or the linear layer, the output f, was required to calculate L prime. Right. Okay, so now we have L prime. And we would just do that by evaluating exactly what L prime is. Say we've stored L prime for, our hinge loss or a categorical cross entropy. Okay, well now if we're trying to calculate this gradient with respect to wjk, we still need to calculate this portion right here, right? still need to calculate the gradient of f with respect to wjk, and then apply the chain rule. So let's go forward in doing that. We already wrote out what this is. We need to apply the linear layer, the betas, to this gradient of h. And the gradient of h, we need the sigmoid prime. Right? And the sigmoid prime requires the fully connected layer. And so we're going to think about this as producing this sigmoid prime of W transpose X plus W naught. So the linear portion of the fully connected layer goes into calculating this sigmoid prime. And then we also, of course, need to calculate this, and then the xk, we'll just write this whole thing out, xk, we'll just write it out here, xk. So this is this will calculate this portion here, this whole portion here. So now we have this gradient with respect to wjk of h, and then we need to calculate the now we need to apply the beta to this gradient, right? And so we would then just take this and apply the beta from the linear layer, right? So the beta from the linear layer goes to these two go into a matrix multiplication, right? Because we have the beta from the linear layer applied to the vector multiplication, or the matrix multiplication applied to this tensor of the h. Okay. So that so that's the next thing is that's calculated. So now we have this partial of f sub theta with respect to w jk. And now this partial f sub theta with respect to wjk, this can be multiplied to the L prime. And so we do another multiplication here. So we call it matrix multiplication. Really, it's a tensor multiplication. If you think about, as soon as you start taking gradients, you get these very large tensors. So, so this is the computation graph for computing this gradient, and the output of this. So we did this matrix multiplication with L prime, and now we're done. This is the gradient that comes out of this. So, so I omitted a lot of the specific details. I mean, the details really are in the math here. We've calculated a way of getting this gradient. But you can start to see that a lot of these things are going to give us patterns. And sort of examining these patterns for how the chain rule works is the magic behind back propagation. So like if you told me, and I had just gone through calculus, take a gradient of this big old function with respect to the w's, these tunable parameters that are at the lowest layer, well, I would just apply the chain rule and be done with it. But the issue is that we want a procedure that's very quickly allows us to switch up our architectures for our neural net. So increasing layers, maybe increasing hidden units. And if I did this, I would perhaps have to, or changing the activation functions. Doing this, I might have to then recalculate this entire, rewrite this whole backpropagation procedure. And but by finding these patterns in how backpropagation works, and really examining how the chain rule works when you have composed tensor operations, we can create frameworks that automatically determine what this computation graph is going to be for a given architecture. Right? And so that's the basic idea behind automated differentiation. This can apply the backprop to automated differentiation can apply backprop to many neural net architectures. Right? So that's the basic idea. And so in theory, all we have to do is specify the components of this forward pass, and then as long as we've cached certain things, such as what is the gradient of all of the activation functions, all of the losses used, then we are going to be able to, using a framework like TensorFlow, be able to have an automated way to construct these compute graphs, which will automatically create the gradients. So that's the basic idea, and that's really what enables the deep neural nets to be easily constructed and trained, is that with these frameworks we don't actually have to write gradient descent type algorithms. All we have to do is specify the neural net architecture, and then TensorFlow or PyTorch will do the rest for us. They'll figure out how to create these compute graphs, and then allow us to quickly evaluate them. So next we're going to talk about a couple of different optimizers. So departing from just vanilla stochastic gradient descent with a fixed schedule, but adding acceleration and adaptive gradient step sizes. And that'll conclude our talk for regarding neural nets.